Okay, so I'm going to talk about some work I've been doing on units of measure. In particular, in the context of GHC and being able to add some kind of system for type inference for units of measure to GHC without actually working on GHC, or working on GHC as little as possible, because GHC is a large and fast-moving program. And so, in the interest of modularity, if nothing else, I want to be able to write my little units of measure system off in a corner somewhere and not have to worry about the compiler changing in a myriad different ways before I get my patch merged and then have to keep up with maintaining it. And more generally, I'm interested in domain-specific constraint solving, so making it possible for programmers to actually have a little bit more control over what's going on in the constraint solver when type inferences happen. So I will very briefly show you the thing I'm talking about. So if you haven't seen, this is where my demo, of course, goes wrong, because worked before.
These meters.
Okay, let's skip the demo in the interest of not having very much time left. So units of measure are things like meters, kilograms, feet. Hopefully you'll be familiar with them from some kind of physics lessons or just general experience. And we want to be able to say in our type system that if I've got some quantity measured in meters and some other quantity measured in feet, then I'd better not be able to add them, at least without doing some kind of conversion. Otherwise I run the risk of making all kinds of nasty errors. And how can we express this in the type system? Well, I'm going to start off by saying let's have a kind of units of measure and some constructors for building up derived units. So I've got one, meaning a quantity that's dimensionless, and then I've got some set of base units, some multiplication operation, which in the spirit of Bob I've written in a symbol that you can't type. And similarly, a division operation for units. So I can express things like meters per second as base m over base s. And once I've got this kind of units of measure, I want to have an equational theory that describes the properties that we expect units of measure to have. And these form a free abelian group. So if I multiply meters by a dimensionless quantity, I would expect to get a result in meters. If I multiply something in 1 over seconds by something in seconds, then I should get something that's dimensionless. And these are just the familiar algebraic rules. And of course, this necessitates some kind of non-structural unification process, because if I've got a constraint that says that u times v equals v times u, which is of course true for all units, I wouldn't want it to be the case that u and v are equal, even though they're both the first arguments of the multiplication operation. So I need some way of plugging in this equational theory. Once I've got my kind of units with its equational theory, then I can declare a type of quantities, which is indexed by those units. So quantity AU means I've got something which at runtime is represented as an A, which will typically just be a single number, but it might be a matrix or something else. And then it's got some units U, which have no runtime significance, but the Typechecker is going to ensure that I use them safely. And then, for example, I can give a unit-safe type signature for multiplication, which just says that if I've got something measured in units U over V, and then I can multiply it by something in units V to produce something in units U.
I have to channel my inner Phil and say, can you explain why it has that type rather than a more interesting, obvious type?
So it's essentially a presentational difference.
constraints.
So it would be perfectly valid to give it the type quantity u to quantity v to quantity u times v. The difference is that if you're inferring the type of a multiplication where you know the type of the two arguments, for example, if you're multiplying something in seconds times something in 1/2 in meters per second, then it's valid to give that the type seconds times meters per second. But in this case, using this type, it will just be presented as meters. It's purely what things look like. So in the interest of time, I will again skip through my nice example of how type inference with these constraints work. Observe that essentially what we want to be able to do is add some kind of user-defined behavior to the constraint solver, which is what the new Typechecker plugins functionality of GHC 7.10 allows us to do. So a Typechecker plugin is a Haskell program written using the GHC API that's dynamically loaded by GHC during compilation, and it has the ability to modify the constraint solving process while the Typechecker is running. That might be, as in the example I'm describing, to implement some kind of equational unification algorithm, or it might be to add some unrelated constraint solving strategy for type classes. So what do these plugins look like? They're given all the constraints that are in scope after the basic GHC Typechecker constraint solving process is finished. So that's some given constraints that the Typechecker knows hold at a certain point, and some wanted constraints that it's trying to solve for, the goals of the proof search process, if you like. And then the plugin is going to either identify that some of the things you're trying to solve are in fact impossible, that you're trying to show that meters are the same unit as seconds, and it can observe that this is impossible and complain. Or a plugin could solve some existing constraints and generate some new constraints that allow the constraint solving process to proceed. How does this fit into the wider constraint solving algorithm in the Typechecker? So what's going to happen is that the main constraint solver built into GHC will run, and if that ends up with some unsolved constraints left over, GHC is going to invoke the plugin that's been registered with it. So the plugin can't change the sort of built-in typing rules that Haskell comes with anyway. It can't change the constraint solving process that's built in, but it can extend it by adding new ways of solving constraints. And then if the plugin discovers an inconsistency, then the constraint solving process can stop. If it solves some constraints, we remove them from consideration. And if it produces some new constraints that it wants to be solved, then we can go back to the beginning and invoke the main constraint solver again, thereby building up this sort of constraint solving process, which hopefully it terminates, although it's quite hard to give guarantees about that. So for units of measure, what this comes down to doing is the plugin is going to look for equality constraints between two types of kind unit. And given those two types, it's going to convert them to a normal form and try to do free abelian group unification in order to solve those constraints. Of course, as we've discussed in various previous talks, it's possible that might get stuck. There are all sorts of interesting, tricky features once you start dealing with real GHC Haskell, as opposed to the sort of the nice simple world of Haskell 98. And so things like type families might be present in the constraints the system encounters. So it just has to be able to say, oh, well, I'll stop, I'll leave this alone, and maybe I'll come back to it later on if I discover some more information which might help me make progress. I won't tell you about the tricky cases. I'll skip straight on to why you should believe one of these plugins if it tells you that your program is well typed. To some extent, you have to trust that the author of the plugin is not doing anything too nefarious, because they could be doing arbitrary I/O during the Typechecker process. But the plugins do have the ability to produce evidence in terms of system FC, GHC's core language, that the constraints they've claimed to solve are in fact solvable. So in the case of units of measure, what this could mean would be writing down the axioms of abelian groups and then showing that any constraint that the plugin solves can be derived from those axioms. It's much like the elaboration process that Edward was talking about, actually constructing the evidence. That, in fact, isn't implemented for the prototyping units of measure plugin I'm describing, but in principle it's that. And to give you some idea of where I'm going with this work, as I mentioned, in principle it's possible to generate evidence, but that's not currently implemented. There are some interesting issues to do with non-termination of type families, which I think that non-termination has come up a few times today, and there might be some interesting issues here. That if you write a type family which diverges, so say loop equals loop times loop, then that allows you to suddenly solve equality constraints which shouldn't be solvable according to the laws of an abelian group. So that leads to some interesting complexities. And as I mentioned, the question of whether, once you've added a plugin to your constraint solver, the resulting system actually terminates is an interesting problem for ongoing work. And I just want to conclude by mentioning a couple of other plugins, these not related to units of measure particularly, but for type level natural numbers or type level integers. So these are using the same interface for modifying the constraint solver, but this time rather than adding units of measure support, they're, for example, allowing GHC to reason about addition, subtraction, other arithmetic operations, which comes up, for example, if you're describing hardware where you want to keep track of the number of wires that you've got going into and out of components, and you want to be able to reason that n plus 0 equals n. At the moment, GHC's got, Haskell's got extremely limited features for doing that. So these plugins are exploring different ways of reasoning about numbers in that way. And I'll stop there. I'm happy to take questions, but I'm also happy to go to the pub.
To go back to your first slide, when you mentioned feet and inches versus meters and whatever the other things are, how do you declare coercions from one unit system to another, or can you not do that yet? So that NASA can talk to ESA.
Which slide were we trying to get to? Yeah, so that's actually an interesting problem. So I do have a way of doing that, but at the moment it requires quite a lot of sort of behind the scenes machinery. So what you can do is you can say, well, I've got one of these units which are sort of somehow abstract in that I can't, in GHC's type system, do very much computation with them. But if I have a way of unpacking a unit as its structure, then I can reason about the structure and then sort of put it back again into a unit.
So you need kind of typeable type class for units.
Yeah, so you need some way of sort of having pi units, basically, being able to pass at runtime a representation of what the unit is that you can reason with, but in such a way that you can't break the unit invariance. That's the overall idea.
Are you doing some sort of imposition of arithmetic behind the scenes, or do you not face the problem that if you compare it from one system of units to another, you may well not have got back exactly where you started?
So the approach I'm tending to take is that you have to explicitly request a conversion between two unit systems, and that's inevitably going to be restricted by the precision of whatever numeric type you're using. So this is sort of parametric in the particular numeric representation type you're using, but obviously if you're using sort of a floating point, then potentially that's going to involve rounding out. So yes, that's why it's sort of explicitly you're having to make that conversion.
Can this also deal with type class constraints? Can you?
So the plugins mechanism certainly can, yes. So if you want to sort of provide a different way of solving constraints for a type class, then that's certainly doable. In this instance, I'm just doing equality constraint solving, it's a measure cover. But, and in some ways, it's simpler if you're only dealing with equality constraints. But yes, you can also do it for type class constraints.
And Fred had some question before?
Yeah.
Because you want, of course, for example, something like meters times kilogram to be compatible with kilograms times meter, you've got this kind of normalization of your units of measures that you've described briefly, I think, or you've mentioned it. And I'm wondering if this kind of normalization can be proved to be correct, so that the normalization effectively preserves the equality modulo the axioms of your theory, like the fact that meters times kilogram is the same as kilograms times meter. So you've implemented this kind of normalization, but are you able to produce the proof, a machine-checked version of this proof? So
I think that goes back to the question, the point I was making about evidence, that in principle there's no reason why you can't at least run, well, during the type checking process, both construct, well, when you solve constraints, construct proofs from the axioms of an abelian group that you've respected the rules. That's not currently implemented, but I don't think there's a particular difficulty in doing that. But of course, that's only proving it for a...
Do you think that it would be possible to expose this proof in Haskell itself, or...?
Well, I say, so in Haskell itself, what you can do is you can write a function which returns a proof, which then, of course, has to be checked. You can't, I don't think you could express in the type system of Haskell, at least not with that lot of work, that your function is guaranteed always to return.
I'm not used to making proof in Haskell, so I mean, I don't think it's a tunnel for this. But.
So you can't.
Oh, sorry. Okay. Yeah.
So you can't give appropriate constants that represent the equalities you care about, and then have your plugin refer explicitly to those constants as proof relevant, as proof that as a explicit proof that the equation holds.
Well, so that's basically what the sort of evidence mechanism is.
Okay.
So these axioms are basically a constant of type something equals something else,
So
which you declare.
So you do give a proof.
So for plugins in general, yes, you can do. Although it's only proving. I think part of the distinction is between proving that a particular constraint you've solved is solved correctly, from proving that your code always generates correct solutions, which is a hard problem. But it's in principle possible to do the sort of simpler version. That just doesn't be used to measure.
There was some question.
Yeah, does it, well, what does it bring you to use this tree-like structure rather than, say, having two lists of base units and then have smart constructors that like combine them, and this way it would compute. So you wouldn't write, you wouldn't have times and divides, etc. You would actually combine the lists. So you'd have the big product at the top and the big product at the bottom, basically. And then it's more well-tagged pattern.
So I think that's sort of doing some kind of normalization at the time that you're sort of writing down types, if you like. Whereas, so this corresponds very directly to the syntax of units of measure, which is...
Do you get better error?
Yeah, which is deliberate in some level for error messages. I really want, and it's a shame I can't demonstrate this now. I really want, if you use something in meters per second where something was expected in miles per hour, I want the error message to say that. I don't want the error message to say that some normal form is not equal to some other normal form when the programmer doesn't know what those normal forms mean. And that's really the benefit of doing this as a sort of plug into the constraint solver over sort of encoding everything using type families. There's some really nice work by Richard Eisenberg, amongst others, on doing units of measure sort of encoded using type families. And that works very well for a point, but where it falls down is exactly this kind of these normal forms showing up in error message.
Can the Typechecker plugins give custom error messages, or does the infrastructure say this and this don't unify? And can you like if the proof fails, is it the new plugin? Can it say why?
So at the moment it's restricted to basically generating the kinds of constraint that GHC knows about. What I'd like to be able to do, and haven't yet, is sort of extend GHC so that you could plug into the error message generation function. And I think that would be independently used.
Interest has that.
Yes, it does. That's why we want to steal it for Aspen.
We've been trying to, I mean, you're very welcome to steal it, in fact we've been trying to throw it. But apparently it's, the error representation is very complicated, so it's more challenging, I gather.
Okay, that's it. Anyone else? Last question. Okay, then that's mine. Well, I was wondering, do you have some way how to impose some domains on different units? Like, if you have, for example, seconds, those might be positive and negative both, but if you have some kelvins, that's just positive number. Can you choose the underlying numeric type under the unit?
So not directly, it's not something I've particularly looked at, but at least at a very simple level, you could sort of do something like you could have a type class indexed by units, and then you could sort of, so you could have a type class of units which were required to be positive from somewhere, and maybe add some type class constraints to get some other way, but that's quite limited. So Bob has some interesting work on sort of relativizing this to different coordinate systems. Bob, you'll have to correct me if I'm mis-summarizing this. But I think what that would potentially allow you to do by having a sort of by having additional indices would be to sort of track things like the different zeros that you get when you're working with different temperature units, for example. And I don't know whether you could do something about it.
Can you just switch the underlying numeric type you are working with, actually?
Yeah, so that's sort of what I was hinting at with type classes. So you can choose the numeric type A, and potentially you could straighten out with the type class to say, I want only types that I want types that contain only positive numbers when I'm using units or something.
Thank you. So you may perhaps use to the before.